Okay, let's do a little recap on magnetic fields and what they actually are because they're kind of invisible. But let's take a look at the first thing we got. We got a compass needle. Compass needle is basically a magnet that's north and south, and the arrow's on the north. What do opposites do? They attract. So this end will always point towards the South Pole. And now presently the Earth, we pretend there's a big bar magnet in the Earth, and this is the north where you live. That's actually the south magnetic field. So that when we stick a compass needle and you're standing somewhere on the Earth, there's the equator, the compass needles always point to the north because they're attracted to the South Pole that's up there. Okay, but that's just the way when the Greeks found these stones, they hung them from a string, and the end that pointed to the north of the world, they called the North Pole. And then after we had more than one magnet, we played around with it, we found that opposites attracted, created a bit of an issue because now, whoa, the North Pole is attracted to the north of the world, but that's actually because the south is up there. Okay, so if you took a look at a magnet, here's a nice bar magnet. There's the North Pole, the magnet, South Pole. It's made out of all those little domains. If I was to drop a compass needle right there, the north part of the needle would be forced away from that north. If I put one here, it would point towards the south. If I put one out here, it would point this way. If I put one here, it's kind of pointing at an angle. Okay, and here, now if I put all these lines in, if I put millions of compasses, okay, they would definitely make a pattern. And that's what you draw when you draw the magnetic field. Okay, it's just throw 1,000 compass needles onto that page, and what would you see? You'd see lines coming out of the north and going into the south. Okay, that's all that means. Okay, so they come out and they come in there. So that's all a magnetic field line. Right here, it's going this way. So there isn't really anything flowing through the air. It's just saying if I dropped the compass needle, what would I see? Okay, so then the other one, with, say we had, see how good my 3D drawing is. Here's a table. Here's a battery. We're going to have a wire that goes through the table, out the bottom, and over here. And let's throw a switch in there. Okay, switch is open. There's no electricity flowing. This is positive, that's negative. And if I had a whole bunch of compass needles, they'd all be pointing the same direction to wherever north is in the world. Okay, so they notice that, and then the guy flicks the switch. We close the switch. All these electrons start firing through the wire. And these compass needles made a cool pattern. Okay, and I'd have to use my left hand to figure it out, but this would go this way. Instead of all pointing the same direction, if you connected all these compass needles together, they'd be forming a circle around this wire. And that wire, if we were to draw it, there's the wire. Let's say it's going to the page here. There's the current going down. You can put your desk here again if you want. Okay, the wire's going like that. To draw the field lines, it's basically compass needles, but you can use your left hand. My thumb will be the flow of electricity through the wire, the electron flow. My fingers, these are the compass needles. So they're going to go like this. So I can see the compass needles are going to form a complete circle around that wire. And that's left-hand rule number one. My fingers will be the field lines. My thumb will be the flow of electrons. Okay, so if we draw just a wire like this, and the electrons are going that way, then I put my thumb on like this, wrap my fingers around that way. So a lot of times it's nice to say up the front, down the back of that wire. So up the front, down the back of the wire, and it forms one complete circle. And then another circle on top of that, another one on top of that. No spiral, just connect them together. That's left-hand rule number one. So thumb is the electron flow, and your fingers are the compass needles, saying which way the magnetism is. Okay, and if it's going this direction, we'll put an X there saying that it's flowing into the wire. If I draw another wire, say the electrons are coming out, then that'll be a dot. And that comes from an arrow. But then this one would be like this. And if I look at that one, my thumb is pointing in the direction of the wire, and my fingers are now going to be the compass needles. They're going to come down the front like that and around the back. So I'm going to make one complete circle and then another circle on top of that, and then go around and around like that, just with your thumb. So down the front would be a good explanation there. That's left-hand rule number 1. Okay, if you look at the magnet though, the magnet picks up things at the ends because there's a big concentration of field lines coming out. Big concentration of field lines going in here. So those are the two sides of the magnet. If I put it near something, it would stick to it. So those type of patterns make a really strong magnet for picking things up. These ones, they don't come out of anywhere. They just make a complete circle. So you can't really pick anything up with that type of magnetic field. If I want to pick something up with it, I'm going to have to coil it. So take like an old paper towel roll and then take the wires. And we're going to wrap the wires around that coil. And across here, I'm going to put a magnet. Put a nice battery in there, positive, negative end. Electricity is going to go through this. So electricity will come out of the negative. If you're doing electron flow, it'll go the other way if you're in the US doing the other type. But instead of looking at, we came up with another rule, but if I just looked at this wire right here, at the top of that tube there, the electricity is going up the back and it's coming out the front. So that'll be a dot. And the next one, there's going to be all these dots. This is just a close-up of the wires there. At the bottom, these guys are going to be all X's. Now, if you go back to the rule from before, that's current coming out, so my thumb is up, so this will try to make a field line like that. This one is into the page, so my thumb is like that. That'll make a field line that goes like that. Tries to make a complete circle, but there's another wire beside it that wound up making these big loops with a bunch of field lines going into the end here and coming out of the other end there. So this is acting like a south pole. So if I was to label this, this is now north, that's south. Instead of doing this first hand rule, we could use our fingers again. Left hand rule number 2. Okay, my fingers will be the electron flow, and my thumb will be the north of the coil. So if I look at this here, electricity is going up here, down the front, back to the battery again. So if I put my hand here, the only way I can grab that tube, pretend the pencil's my tube, my finger's pointing down the front, my thumb is now on this side. So that will be the north side. Okay, and that'll be south. That's left-hand rule number 2. If we do another coil, here's another tube. I'm gonna wrap the wire the other way this time. It's gonna go up the back, down the front, and loop around, and back like that. And even if I put the battery the same way, plus minus, now the electricity is going up the front and then scoots down the back and back to the battery again. So this time my hand is now going to be, fingers are up the front, down the back. Now this will be the north side over here. So that left-hand rule tells you which side of the coil is north or south. Okay. If you're American, I can draw the exact same one as here. There's the same tube, and the wire went up like this, around like that, down here, and they have positive, negative. Let's do conventional flow. Okay, 200 years ago we thought the positive slow. We now know it's different, but some people still like to do it the other way. So this will go up like that, and around, and then the imaginary positive charges will go this way. Okay, if you're going to look at it that way, you have to use your other hand. You can use your right hand, and my fingers are going to go up the front, down the back, and my thumb is on this side, so this will be north. Okay, exactly the same as you got up here. Here you were thinking electrons, you use the left-hand rule. Here you're thinking positives move around. Then you can use the right-hand rule. Same thing, just the other hand. It's not like if you drove across the border into the US, just because they think the electricity is positive flowing, it's not going to change. Magnets aren't going to work the opposite way. Electric motors aren't going to spin backwards. You can't take a drill across the board and the drill doesn't work anymore. So left-hand rule number 2 is for coils. Okay, and the last one is left-hand rule number 3. Left-hand rule number 3. And again, it's a shortcut to take a look at something a little more complicated. Let's say this is my north and a south. This is a horseshoe magnet. It's actually in 3D. I guess we can kind of sketch some of it in 3D here. Okay, so there's a north and a south. Okay, I'm gonna put a wire inside the magnet. That's really nice if we're in the classroom because we can actually do this. And then we'll put a flow of electricity that way. And that wire, in class, I'd flick the switch and the wire would either jump right out of the magnet or get pulled deeper into the magnet. And sometimes this is called the motor principle because you're making something move with electricity. Okay, but again, we can look at this. This would be an X at the end of the wire. So if I just go back to 2D, I'm looking straight at this thing, north, south. There's a wire in here with a current flowing into the page. Okay, you can go back to your left-hand rules, into the page, left hand, the one with the watch, stick the wires down, and these guys are going to be going around this way, which is counterclockwise if you know about those clocks. And then we have north to south. There's a magnetic field created by this magnet. Those lines would be straight though. But if I look here, these lines are the same. These ones are opposites. And guess what opposites do? Opposites attract, like fields repel. That wire is going to shoot deeper into the magnet. Okay? So instead of looking at left-hand rule number 1, we made up a new rule and we said, okay, we got an open hand. So thumb is the electron flow. My fingers are the magnetic field from the magnet. Okay, from the magnet. Okay, so that's going to be north to south. So my fingers are going to point up. My thumb is the electricity. Electricity is going into the board. So my thumb has to go this way, hands like that. If you ever push anything, you push with the pad of your hand, like you push forward. So this guy's going to get pushed into the magnet with an open hand. Some people do this, they drop a finger and they say it'll get pushed like that. This tells me the direction of the force. I just know I push with my hand. If I fall on the ground, I put my hand out to stop myself. If I fall on the ground and I put my hands backwards to stop myself, that's not going to work out too well. So left-hand rule number 3, my thumb will show the direction of the electrons, and my finger will show the existing magnetic field, and you'll push with the pad of your hand. Okay, push with the pad of your hand. And that would be left-hand rule number 3. And then if you want to go ahead, we'll do Lenz's law then. Let's take a look at, we have a coil. I can wrap a bunch of wire around the coil. But this time, instead of a battery, it can just be a straight wire, or we'll put a light bulb in here. And I'll put another magnet here. And let's say someone is shoving that magnet into the coil. While that magnet is moving, the light bulb comes on. If I just put the magnet in the coil and let go of it, the light bulb doesn't work. But if I pull the magnet out, the light bulb comes on again. So we know now that we're making electricity by moving a magnet. It's like the old energy unit. Work equals force times distance. So I'm applying a force on the magnet into the coil, and that force is turning into electricity. But sometimes we need to know which way the electricity is going, because this is going to create a magnetic field. So when I push this in, if this became a south pole, I wouldn't need any force. The magnet would just fly in by itself, and that's not happening. Okay, if it did happen, that'd be pretty cool, because then I'd make basically a gun. Bring the magnet close to the coil, it would get sucked right through there, and the light bulb would come on. So we're actually accelerating the magnet and making free electricity. That's 2 sources of energy coming from absolutely nowhere. That's not going to work at all. So it's got to be, this will be north to fight whatever I'm trying to do. If I'm shoving north pole into the coil, that'll become north to push against me, creating a force that I need to apply over a distance, and that work will turn into electricity. Okay, so it will fight you. There's like the Wattman short version of this sort of stuff. Okay, so if I have another coil, okay, not even put a light bulb or nothing in there, and we'll just say we have another magnet here, and that magnet is inside the tube. This is north, that's south, and someone is in the process of pulling that magnet out of the coil. Electricity is going to come on, so if this is moving away, this is going to fight me, which means this would have to be north to try to stop me from pulling the magnet away. Okay, so that's how you determine which end is north and south. It just fights you. If I'm shoving north in, that becomes north to try to stop me from coming in. If I'm pulling south out, that becomes the north, try to stop me from pulling it out. And if you want to know which way the electricity is going, you got to go back to rule number 2. Okay, so that's north. If that's north, my fingers are going up the front of the tube and down the back. So up the front, down the back, across the light bulb. So it's actually traveling to the left through the light bulb here. This one, north is on that side now, so I put my fingers like that. Fingers point down the front. Okay, so across this way, up the back. So that way the electricity is flowing to the right of the base there. Okay, whether you use conventional or electron flow is fine. But just remember that on the test it'll say electron flow. If it's the textbook is all American, it's all conventional flow. So those are the rules. We got left-hand rule number 1. If we recap, rule number 1 is your fingers of the compass needles and your thumb points in the direction of the electron flow. Left-hand rule number 2, your fingers show you the current and your thumb will point where the north and south is. Rule number 3 is when there's two fields fighting each other, and that one is an open hand. So my thumb is the flow of electricity, and my fingers are north to south, so you could write a north on the pad, south on there, and your thumb is the electron, and then you push with your hand. And this is Lenz's law. It just says if you're making electricity from magnetism, the field you create is going to fight whatever you're trying to do. Okay, so if I'm pushing north in, that becomes north to try to stop me. And field lines, they basically just say, which way would a compass needle point?